Everyone, we'll be going over problem number 704, binary search, today. We'll start with the problem readout, do a whiteboarding session, and then finally write out the code for the solution. So let's give this a read. Given an array of integers nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index, otherwise return -1. You must write an algorithm with O of log n runtime complexity. Right? So basically, if I look at the examples, they will give me two arguments. The first will be a sorted array, and then the other one will be a target. And if the target is in the array, I would have to return the index of that target. So 0, 1, 2, 3, 4, which is the fourth index. So I return 4. In the second example, I have the same input as the first one, but the target is 2, but 2 isn't in the array, so I return -1, which signifies that the target is not in my input array. Now, if I look at the constraints here, the array will be between 1 and 10 to the power 4 elements. Each element will be between -9,900 to 9,999, and all the integers in nums are unique. Nums is sorted in ascending order. All right, so let's talk a bit about binary search. What is binary search, right? So the idea here is we want to narrow down our search space by half every single time we perform the operations inside a loop. So for example, if I were to do a linear scan of the array, so an O of n algorithm, I would have to check every single element until I found my element. For example, in this case, my target is 9. I would have to start at this index, and then I have to check every single element. So I would do, is -1 equal to 9? It's not. So move forward. Is 0 equals to 9? It's not. Move forward. Is 3 equals to 9? It's not. Move forward. Is 5 equals to 9? It's not. Move forward. Is 9 equals to 9? It is. So we have found our answer. But imagine if we had a really, really big array. So like thousands of elements or millions of elements. I would have to go through every single element to see if it is in my array. Right? So we don't want an O of n algorithm for this. We can use the fact that the array is sorted to our advantage and perform binary search. So how would binary search look like? So imagine instead of starting at the first position, we would have two separate pointers. So we would have the left pointer. Oops, maybe I'll draw this better. So we would have the left pointer and the right pointer. So the left pointer would start at the first index, which is 0, and the right pointer would start at the last index, which is 5. The idea here is we will calculate a middle position based on these two indices. So 0 plus 5 divided by 2 is equals to 3.5. Oops, 2.5, right? 2.5. But we have to round down because indices are integers. So 2. At 2, we have the value of 3. Now at this point, I can check if 3 is equals to 9. It's not equals to 9. Now I check whether 3 is less than or greater than 9. So I see that 3 is less than 9, which means everything from the start of the array up to 3 will also be less than 9. Because this array is sorted, everything left to 3 will always be less than 3 itself, which means we can eliminate all these choices, right? So if I eliminate all these choices, I've narrowed down my search space by quite a lot, right? So that means I can move my left pointer to this position now. Right? So this 2 was my mid index, right? So this was my first mid index. So this was my mid index, and then I moved my left pointer to mid plus 1 because everything up to and including the middle element was less than my target. Now I do the same operation again. So now my left pointer is at the 3rd index and my right pointer is at the 5th index. So I do 3 plus 5 by 2, which is equals to 4. So if I do 4 and if I go here, this is my new mid index, right? So this is my new mid index, and then I see that this is equals to 9. So I get my answer, which is 4 in this case. Now, what if we had to find a higher target, right? So for example, if we had an array of 1, 2, 3, 4, 5, and we had to find let's say 2, right? So our target would be 2. Our target would be 2. We'll do something similar as well. So this is the 0th index, this is 1, this is 2, this is 3, this is 4. So I would start here, I would start here, and then I would do 0 plus 4 by 2 is equals to 2, right? So my mid index is 2. Now I check, is 3 greater than, or is 3 greater than 2? It is greater than 2, which means that everything from 3 up to the last index will also be greater than 2. So we can get rid of all of these choices, and we would move our right index to left of my current mid, right? Which would give me, which would give me this new index, right? So I will do the calculations again. So 0 plus 1, 0 plus 1 by 2 is equals to 0.5, but we have to round down, so it is 0. Now this is my mid, so I check, is 1 less than greater than 2? It's not. And then I check if 1 is less than 2. It is less than 2, which means I can get rid of this. So I move my left pointer 1 step after the mid. Okay, now they're both at the same position, so I would do 1 plus 1. So 1 plus 1 by 2 is equals to 1, and the element at index 1 is equals to 2, which is equals to my target. So I would return 2. I would return 1 because that's the index of the target. Return 1. Alright. So the reason why this is an O of log n algorithm is because every time your input doubles, the number of operation it takes to get the answer increases by only 1. Because you're getting rid of a lot of the like half of the elements every time you perform this operation, it makes it a lot easier or a lot faster to find your target element. And we can only do this because the array is sorted, right? So let's try coding this out. So first I started by initializing the left pointer to the first index. Then I initialized the right pointer to the last index, which would be nums.length minus 1. Then I performed my operations until the left pointer was less than or equal to r, because if it overlaps, then I would I would go into the territory where I've already excluded the possibilities. So my while would be less than L is less than equals to R. And then I'll have to calculate the mid. So in our case, we did const mid is equals to, we added L plus R, then we divided it, and then we rounded it down. So in JavaScript, that would be the floor function. So you can round this down. And then I checked whether my number was greater than the target, right? So I did nums mid is greater than target, then do something here. Else if my nums mid is less than target, do something here. And then if my number is equals to the target, then I would just return the current index, which is mid, right? So what did I do when my current number was greater than the target? So if my current number was greater than the target, I excluded everything from that position up to everything up to the last position, or rather everything right to it. So I moved my mid index from my current position one step to the left. So I would have to do R is equals to mid minus 1, because I'm excluding everything starting at mid to everything that's right to the array, all right? And when my number was less than target, I excluded everything from start of the array up to the middle position. So I would do L is equals to mid plus 1. And then finally, if I don't reach the condition where my number is equals to the target, I would do return minus 1, right? So let's run this and see how it goes. It's 4 and 4, okay? So if I submit the solution, and it passes, right? If you want to look at a visualization for this, I will leave this in the comments. So hopefully you can see how it goes. So for example, if I want to search for 374 and do a binary search, notice how it's doing the search, right? So it's eliminating a lot of the possibilities. If I use a very large array now and search for 374 again, you'll notice that it is still very, very fast, right? Now 374 isn't in this array, so we'll get minus 1, but it did search the entire array very, very fast. If I were to do a linear scan instead, notice how slow this moves, right? So if I skip forward, like this is very, very slow, right? So hopefully that helped you understand how binary search works and what exactly we're doing. And if you have any follow-up questions, please feel free to ask them in the comments. Thank you for watching.